Hello, hello, hello. Is it working? Oh yeah, like this. All right. Hello, everybody. Thanks for coming to my talk. I'm going to be talking about my package ecosystem, really, RunwayPNPSolve. And just a few notes about me. So I'm a PhD student at the Stanford Intelligent Systems Lab, and this project was done in collaboration with the Airbus kind of Silicon Valley campus. And there's also a paper out for this, which I'll talk about a bit later. But yeah, let me maybe briefly talk to you about the problem that we will be discussing today. So the PNP problem, what does it stand for? PNP is the pose from endpoints, right? So the problem we're trying to solve here is you are in an airplane and you have a camera and the camera looks at the runway. And now you assume that you have some kind of model that looks at the image here and actually finds for you where the corners, for example, or some other image features are located in the image. And so what these companies these days do, like Airbus and Boeing and many others, is they try to use some kind of neural network, right? And now the problem is that there's always some uncertainty in actually exactly where the corners are in the image. And so, for example, there can be pixelation or there can be other problems. And so what we also assume is that you actually have the neural network that gives you some of the uncertainties that it thinks where these points are located. And we can talk some other time how you can achieve this, but it's possible. And now our problem is how do you actually compute probabilistically where you're located and to compute a probability distribution over your pose given these probabilistic inputs. So this is the first problem that we wanted to solve. And then the second problem, which we'll also briefly be discussing, is so now I built for you a system, and that gives you these probabilistic estimates. So it's Gaussians, right? We're engineers here. We like Gaussians. And so I have some system, and it gives you Gaussians all the time. And now I ask you, okay, are you actually sure that these Gaussians are like a correct representation of the uncertainty somehow? So there's this question of like, how do you measure correctness of a probabilistic estimate if you only ever can measure one time? So another example is somebody tells you the probability of it raining tomorrow, but you can only measure one time if it rains tomorrow or not, right? And so you can kind of do this many times, but it's not so easy to find out if your probabilistic estimations are actually correct somehow. And so this topic is called calibration, and we'll also very briefly talk about calibration. So there's a paper which I put in last week. So you can find it in the resources for this talk. I'll put it on archive after this conference, and then it will be published at Digital Avionics Systems Conference. Maybe I'll see some of you in San Diego in September. And then today I'll be talking actually about some specific parts of the ecosystem, mostly two packages which are registered right now, which are Probabilistic pose estimators.jl and multivariate normal calibration, which are kind of solving this problem I was just discussing. And then I do want to take a minute or two to talk about some kind of more Julian thing, what we try to do, which is how to have a very strongly typed type system where you can have interfaces for your users that kind of require certain unitfulness, certain coordinate systems, and work with gradient descent-based methods. Great, so we don't have so much time, so we'll be a little bit fast. There's this package, Probabilistic Parameter Estimators, and this solves this kind of pose estimation under uncertainty. And so you can actually phrase this multiple different ways. And so we implemented 3 different estimators. There's an estimator which is based on kind of least squares minimization using the SciML nonlinear solve. You sample noise many times, so you kind of assume some noise model, you sample it many times, you solve it many times, and then you have kind of a sampled representation. There's another way which you can phrase this as a probabilistic program using Turing, for example. I don't know if there's any Turing enjoyers here tonight. But this also works quite well. And there's also a much faster kind of mathematical approximation looking at the Jacobian directly and mapping the uncertainties in kind of one step. And so in this paper, we kind of explore when these methods are good, when they're bad, for example, when the linear approximation performs poorly and when you need to use something else. And also we explore about actual runtimes. So now you wonder, can you run this on a real-time system, such as an airplane, right? And so we find that these methods for one kind of pose estimation and uncertainty take somewhere between half a millisecond to 200 milliseconds. So even in the expensive case for LSQ estimator, you can do it in theory 5 times a second on some normal chip. And in the end, I'll also very briefly talk about kind of getting this onto an airplane using a C API. Great, and so if you want to use this, we can't go to all the details right now, but basically in the end there's just this predict dist function, predict distribution here, You put in your estimation method of choice. You put in the projection function, which can actually be many different functions. So you can also have, for example, the angles of the sightline, which are predicted by your machine learning model. You can have other image features or the horizon line. It doesn't really matter. And so you put this kind of function here. You put your knowledge about the world here, and then you kind of solve it, and you get a nice distribution. So I hope this is maybe useful to some of you. Here's also a little teaser. We'll talk about it a bit more in a second. But you can see that these runway corners up here, they are like already very strongly typed, and we'll talk about this. Great. So then the other package which is registered, which you can use today, is this package trying to answer the question, how do you measure kind of quality of your uncertainty predictions? And this quality, and the statisticians, they call it calibration. And so for multivariate distributions, calibration is a little bit poorly defined. Apparently the statisticians only care about univariate things, but we want to maybe have the whole 6 degree of freedom pose or 3 degree of freedom or something. And so we came up with a little theory, and it's in the paper, and the implementation is quite easy. And in the end, you just need this one function. So if you have some system that you use that predicts these Gaussians, and you have kind of ground truths that you can compare against this, all you need to do is to get your your predictions together. You can just compute this. Well, you can call this compute calibration method. It will work it out internally, and it will give you some kind of metric of it's good or bad. You can plot it, and basically, if you plot both of the outputs that come out against each other, and they are like nice and diagonal, then you know you did a good job. And so, okay, you can read the paper to figure out if this is a good job or not. So are we doing for time here? Okay, we are progressing with time fast. So then I do want to talk about something which is currently unregistered, but it's kind of a close to my heart topic, which is this idea that especially if you work with Europeans and Americans, there's always this question, oh, is this in feet? Is this in meters? Is this in degrees, radians? Even though I tried so hard to make this unambiguous, we've had so much trouble. I'm sure everybody here has had trouble like this. So what you really want, and what you maybe want to use Julia for, is to use the type system to kind of make very clear interfaces so that the user cannot possibly mess it up. That's your dream at least. And so we were exploring a lot how to kind of use the Julia type system to get both of these constraints, to get two constraints satisfied at the same time. So we came up with a solution how you can define coordinate systems. So XYZ here is a coordinate system that is kind of aligned with the runway. And so whenever a user wants to put a number in, like a runway corner or something, he has to explicitly say, I want this to be an XYZ coordinate system number. So now it's already clear, which coordinate system you're in. Then we use unitful. Maybe some of you have used unitful before to kind of specify which unit meters or whatever it needs to be. So also, again, the user needs to explicitly say, yes, this number I'm putting in, it's in meters. And the function says, I expect meters. The problem why this is not so easy and why many other languages can't do this is because you still need a lot of flexibility. For example, if you want to auto-differentiate through this, you need to have, actually inside of this XYZ meter thing, you need to have a dual number, which is, again, a new type. So now you have these constraints from two sides. You want to constrain coordinate system, the unitfulness, but you want to be flexible with respect to the kind of actual number type, if it's a float or something else, or dual type. And so we kind of came up with a way to do this, and I think this is I would love to talk about this, and I think the world needs more of this. And so this kind of works, and I would love to see people use this. Just one last thing before we're out here. So this is kind of between the company and us, but I do want to say that we also managed to now take this thing and compile it to a C library, because of course companies are like, oh, Julia, that's all nice, but how are we supposed to put this on an airplane? I cannot upload the Julia compiler or whatever. And so we managed to use the package compiler and actually expose it as a C library. And now, they may or may not put this on some airplane and kind of test it out in production. Of course, I'm not saying this is a thing they can sell, but this is a thing they can now at least try out in some kind of more closed system. And so I think this is very exciting. And I do think at this JuliaCon, there's like a lot of talks actually about this. And I think this is, the companies like want this and this works. So it's pretty cool. And I hope you can pitch it to your next project manager that you say, well, I do this Julia code, but I promise you at the end, I will give you a C library and you can integrate it to your system. Okay, that's it, thank you.
Thank you for the great presentation. I wanted to ask you about the unitful thing. Could you quantify the impact on the performance that it has, like the constraint on the type?
Do we have a second mic? Yeah. I see you. Second mic.
Oh, that's fine.
Okay. All right. Thanks. Yeah, so that's a good question. And also when we were wondering, so the reality is right now, all the performance critical parts, for example, the nonlinear minimization, you actually just strip the units before. Okay, so yeah, it's a bit ugly, but it's kind of fine. It's like an implementation detail, and then you don't lose any performance, or I mean, you know, it's a very small performance loss. And so we were also experimenting. So actually, it works to put even unitful things into many different algorithms. But some of the, for example, if you have a matrix of unitful type and then you do matmul on this or autodiff, it is significantly less efficient. And so in the end, you kind of identify where are your hotspots, and there I recommend taking it away. But the operations mostly work, so even if you wanted to do it, it would be fine. And yeah, so this is a compromise that's reasonable, I would say, that you say at your hotspots, you make sure that it's fast, and otherwise you keep your unitful interface.
Can I ask the question? Yeah. Yeah, thank you. Very nice talk. So the approach I'm more familiar with the geometric problems is to use inerranza loop, because basically those are polynomial equations. If you write the correspondence between points for those geometric problems, PMP, F matrix, E matrix, whatever. In general, the approach I'm familiar is that in a Ransack loop, you solve the determined, not overdetermined system of polynomial equations, and then you, by iterating in a Ransack loop, you filter out liars and inliers and get estimate. So my question is, how does this approach compare to that?
So I think one of the kind of key differences between Ransack or whatever is that we kind of want to use all 4 points. We don't really imagine there to be any outliers. So as far as I know, Ransack kind of deals with this first and foremost. And then I'm not sure, in fact, I'm quite sure that such an approach doesn't really give you a distribution of your minimum. So that's really... Okay, so I'm not familiar with this, and I would be happy to see it. And so if you solve it in a similar way, what I think we should do is, I solve it this way, you solve it this way. Then we put it into our calibration measurement device, let's say algorithm, and we'll see which one has the more truthful probability predictions. And then also which one has the so-called sharper predictions, so basically the more concise Gaussian, because actually you can be calibrated but very imprecise. We can talk about offline. So I would be interested to see other methods that try to solve the problem. Yeah. Thank you.